Okay, we're going to now pick up with the subjective sound or perception portion of our discussion. This is sometimes called psychoacoustics. We want to start by talking about the mechanism of hearing, so we're going to talk a little bit about the anatomy of the ear. We divide the ear into three separate sections. The outer ear, which includes the pinna, the auditory or ear canal, and the outer portion of the eardrum. This is the visible portion of the ear that we can see when we're looking at someone's head. Next, we have the middle ear. This is an air-filled cavity behind the tympanic membrane or the eardrum. And the parts that we are mainly concerned about in the middle ear are the three small bones called the ossicles. In terms of trivia, these are the three smallest bones in the human body, and they are called the malleus, the incus, and the stapes, sometimes called the hammer, anvil, and stirrup, which are descriptive names for what they look like. Finally, in the inner ear, we're most concerned about the cochlea. However, this also includes the vestibule and the semicircular canals. Those are more directly related to balance, so in our discussion of hearing, they're not as much interest to us. So in understanding human perception of hearing, we need to understand that the outer ear functions to bring in these sound waves, these variations in air pressure, to our eardrum. The eardrum reacts to these changes in air pressure by moving one direction when we're in a compression part of the waveform and moving the other direction when we're in rarefaction. The eardrum is connected to the three small ossicle bones, which then move in response to the eardrum's movement. The three bones are arranged such that the movement of the tympanic membrane causes movement of the malleus, incus, and the stapes. When the stapes moves, it pushes on the oval window of the cochlea, which causes movement of fluid within the cochlea. As the fluid moves, small hair cells within the cochlea called cilia fibers will move. Now these hair cells are the acoustic sensor cells. When they move, they produce electrical signals, converting the vibrations in the fluid within the cochlea into electrical potentials which can propagate to the brain as nerve messages. So let's move on and let's talk about the 5 human perceptions of sound. Generally, we will define these as pitch, loudness, timbre, duration, and location. You may notice that these bear some similarities to the 5 physical attributes of sound that we talked about in the previous acoustic lectures. Let's begin with loudness. Loudness is the human perception of amplitude, and it's measured in a unit called phon. So the dynamic range for human hearing goes from the threshold of human hearing at about 0 dB SPL to the threshold of pain, which is going to be in the 120 to 130 dB SPL range. Again, this covers a range from about 20 micropascals to about 64 pascals of pressure variation. However, on the psychoacoustic side, we need to understand that perception of loudness is not linear. We also need to understand that we are not as sensitive at all frequencies across the human perception range. Human beings can hear from a frequency range generally cited from 20 Hz to 20 kHz. Of course, the older you get, the more we tend to lose our high-frequency hearing response, so by this point in most of your lives, you probably do not hear accurately up to 20 kHz. However, within that range, we are most sensitive at about 3.5 kHz, and we become increasingly less sensitive as we move into the highest and lowest regions. What we're seeing right now are the so-called equal loudness contours. These are also sometimes called Fletcher-Munson curves. However, the modern equal loudness contours are a bit more accurate in that they involve a significantly greater number of participants. So I want to talk you through what we're really looking at on these charts. On the y-axis, we see sound pressure level in dB/SPL, and this correlates to the location on each red curve at 1 kHz. So you notice on the 60 red curve, here in the middle of the screen, at 1 kHz, we are at 60 dB/SPL. We would call this the 60 phon curve. What this graph is showing us is the amount of boost or cut above the level at 1 kHz that we need to apply to perceive these frequencies as equal to 1 kHz. I'm going to explain that a slightly different way. If we were to play a 1 kHz tone, and then we were to play a 100 Hz tone, and ask a participant to adjust a volume control on the 100 Hz tone so that they perceived it at the same level as 1 kHz, what we would find is that they would need to significantly boost it to perceive it at the same level. If we were to play a 1 kHz tone and then play a 3 kHz tone, we would find that we'd need to turn the 3 kHz tone down to perceive it at the same level as 1 kHz. If we were to play a 10 kHz tone, we would have to boost it above 1 kHz. And if we were to take this test and test a variety of participants, we would get a curve something like this. However, an important detail that we want to understand is that if we were to start at a different SPL level for our 1 kHz tone, say at 80 dB SPL, we get a slightly different curve. And you'll notice the general trend is that the more quiet we start, the more extreme the differences between the lowest frequency range, the mid-frequency range, and the high-frequency range become. As we get into the louder and louder range, we find that this curve starts to flatten out a little bit. So some key items to take away from this. The human perception of loudness is impacted by the frequency of sound. Some frequency ranges require greater amplitude to be perceived as having equal loudness. The precise relationship, however, between these frequency ranges depends on the overall loudness at which we're listening.